Hello, I'm Ramya Hebbala-Guppe. We present our work Stitch in Time Saves 9, a train time DNN calibration technique. This is a joint work conducted at IIT Delhi with Jatin, Neelab and Professor Chetan. Despite the wide applicability of DNNs as a part of decision pipelines in safety critical applications, modern DNNs are found to be poorly calibrated. Figure A compares a 7-layer LENET with 110-layer ResNet. Top row depicts the distribution of prediction confidence as histograms, and the average confidence of LENET closely matches the accuracy, while the average confidence of ResNet is substantially higher than its accuracy, showing miscalibration in modern DNNs. Figure B shows reliability diagrams that plots accuracy as a function of confidence. A well-calibrated model is an identity function. Bars below x equal to y line imply overconfidence and the bars above imply underconfidence. On the right, we list the factors that affect calibration in DNNs. We have a classical multi-class classification setting with outputs y hat and p hat as output label and its confidence. A top label calibration operates solely on the winning class. We propose to adapt top label calibration to a multi-class setting where we calibrate the entire probability vector. As a contemporary calibration techniques leave the confidence of the non-max classes for calibration. Commonly used metrics include EC and SC. EC is a weighted average of all the gaps in the winning class, while SC is the class-wise extension for every class. We justify the need of multi-class calibration with an example of an AI-assisted diagnosis system that says 50% chance of patient having a benign tumor and 10% chance having an aggressive form of a cancer and 40% chance of other conditions. Doctors would be interested in miscalibration of each class before any intervention or informed decision is taken. Researchers have tried to address miscalibration by learning a post hoc transformation of the output vector. However, post hoc methods involve post hoc training calibration on the holdout set, whereas trainable methods calibrate during the training procedure itself. Our approach is a train time one without the need of a holdout set, making the deployment more practical. Being a train time approach that optimizes calibration and accuracy jointly, we call it Stitch in Time Saves 9. We propose a multi-class difference of confidence and accuracy computed on a mini batch during training. It is inspired from SCE metric, but it overcomes the non-differentiability due to binning. It can be applied to a batch-wise setting and can easily be back-propagated with the additional main classification loss term to jointly optimize accuracy and calibration. We want the average prediction of a prediction confidence of every class J to match the average occurrence in a data distribution. We validate our technique by performing experiments on the benchmark datasets and diverse feature extractors. We select FL plus MDC as our approach based on the reliability metrics ECE and SCE. Table below shows the approach exhibits least calibration error. We report the calibration at a class level on SVHN. Our method gives the best scores for all but 3 out of 10 classes where it is the second best. We observe similar performance on CIFAR 10. Reliability plots depict well-calibrated probabilities of our approach unlike others. Our proposed approach gives a low confidence for incorrect predictions, and reliability diagrams show we mitigate the overconfidence and underconfidence from NLL and LS training respectively. We achieve the least calibration error in both the cases, dataset drift and imbalanced datasets on the majority of the cases. In semantic segmentation, quantitatively, we see a significant drop of EC/SCE when compared to focal loss and TS, which are the state-of-the-art methods, by a factor of 2 and 40% respectively. Qualitatively, our approach is better calibrated than temperature scaling, as evident from the qualitative results shown in the picture. Our goal was to mitigate miscalibration of DNNs to enhance trust and interpretability. This is done via proposing a train time auxiliary loss, MDCA. MDCA offers state-of-the-art performance and it offers promising results on long-tail datasets and NLP tasks and image segmentation. Thank you for listening.